Unit 2 test for geometry, reasoning, and proof. So here are some examples. You found the video. I'm also going over this in class. I'm giving you a full day of class to work on it and 2 days to complete. So you should use this. How do you use this help document? It's going to be a long document, but you need to pause, stop, fast forward, rewind. Use this to help you with answering questions. On the second page, you do see definitions. These are general geometry definitions. If you want to see the definitions of the postulates and theorems, you can click on this link also in the document. Number 1, select each statement that represents inductive reasoning. Inductive reasoning starts with observations and works towards a broader theory. So it says to select 2 answers. In these 4, which I will read, we're going to look for an observation and a theory of something that might happen, probably will happen in the future. We're not sure. It hasn't happened. It's not for sure. So inductive reasoning, we're going to start with an observation and then work towards a broader theory. So number 1, Jeremy can buy a car if it's priced at $8,000 or less. The salesperson shows him a car at $7,195. Jeremy can buy the car. So that is not something that we're going to infer or make a theory about. That can happen. Jeremy has only owned yellow cars. His neighbors expect him to buy a yellow car. He hasn't bought a yellow car, but he always has yellow cars. If he's buying a new one, his neighbors are going to they have a broad theory. He probably will buy a yellow car. So I believe that's one of them. Letter C, the first 4 cars that Jeremy sees in a lot are priced above his budget. Therefore, he expects all the cars in the lot to be priced above his budget. He's assuming, making a theory, that I can't afford anything in here. So that one, I believe, is inductive reasoning. The last one, Jeremy saved $100 a week for 80 weeks. Therefore, Jeremy saved $8,000. That is something that happened. That is not inductive reasoning. So the 2 statements for this example, number 1, are B and C. The next one, you guessed it, is deductive reasoning. So these are the same examples. I'm not going to read over them, but deductive reasoning starts with facts, proven ideas, and narrows down the result to a specific conclusion. So A and D, they are specific numbers. Letter A, there's a car he can buy at $7,195. That will happen if he would like to. Also, he saved the money for 80 weeks, and he has that money. That is something that happens. That is deductive reasoning. Identify the hypothesis and conclusion for the following conditional statement. If Mrs. Phillips makes coffee, then she starts her day with a rich morning blend. So I've highlighted on here the hypothesis is the words after the if. Not including the if, the words after if. That is the hypothesis. Then she starts her day with a rich morning blend. So you're going to select the 2 correct answers. So the hypothesis is Mrs. Phillips makes coffee. That's the hypothesis, not the if. The if is not included in your answer. Just anything after the if. The conclusion, anything after the then. She starts her day with a rich morning blend. Be careful with this one. Now we want to do the inverse, converse, contrapositive, biconditional, or counterexample. So we have all of these. Here's the definition of them. The converse, you're going to take your statement and switch the if and the then. So if she starts her day with a rich morning, if Mrs. Phillips starts her day with a rich morning blend, then she makes coffee. Right here. So that's the converse. You can go read through these, the inverse, the contrapositive, and it's also asking for biconditional. Biconditional is this statement right here, if and only if. If you see those words, that is biconditional. Mrs. Phillips makes coffee if and only if she starts her day with a rich morning blend. Also, a counterexample is anything that makes it not true. So in this case, Mrs. Phillips had V8 this morning. So that makes it not true. But again, take your time, pause this, read through these, make sure that you see, you might even write them down. Write down your hypothesis and conclusion, and then you can use these definitions and move them around. So that's number 4. Number 5 is a proof. We are given that A, this line A and line B intersect. We want to prove that this angle 1 is congruent to angle 3. I will read the proof. Keep in mind you have blank 1 and blank 2. We have these things to look for to put into the proof in these spots. So because line A and B intersect, angle 1 and 2 form a linear pair. If I look here, this is true. 1 and 2 form a linear pair. And angle 2 and 3 form a linear pair. 2 and 3 form this linear pair. By the, what? How do we know that they form a linear pair? We have a definition of linear pair, and that is the answer. If we look at linear pair postulate, definition of supplementary, transitive property, subtraction, so we're not subtracting. We're not using the transitive property. They are supplementary, but we haven't got there yet. We're just saying that they're a linear pair. So the definition of linear pair goes right here. So then it says the linear pair postulate states, now that would be a clue that you're not using this linear pair postulate in here because they wouldn't reiterate it. So they're saying that the linear pair postulate states that a linear pair of angles are supplementary. So it gives you that definition right here. We don't see their supplementary up here. We just see they form a linear pair. And so the definition is here. So you know it's not linear pair postulate. The equations measure of angle 1 plus, now this is angle 1, plus the measure of angle 2 equals 180 degrees. Measure of angle 2 plus the measure of angle 3 is also 180 degrees, are created using the definition of supplementary. So you see that 180 degrees, you should be looking for the word supplementary. Now you can read through the rest of the proof, but we did not use, so this transitive property, they talk about it down here. Subtraction, we haven't subtracted. So this one, number 1, is definition of linear pair. Number 2 is definition of supplementary. Number 6 is the last problem. You will be given a proof, and it would not be this big, but you will be given statements, and you have to provide the reasoning or provide the statement if it has a reason. You will have a bank of answers to fit in here. And let's just look through them. So we have 3 sets of equations, 3 blanks here. So these 3 equations will go here. Most of the time, if we're simplifying and we're proving something, this will go way down here. So I could even cross that off and move it down here. Given always goes at the top. So we're given this statement. And then we are left with 2 less than we started with. So how do I get from number 1 to number 2? What is happening? If you look at the math problem, we are doing a distributive property, 3 times x and 3 times -4. That's the only thing that has changed between 1 and 2. So distributive property would go here. What are we doing in the math problem from number 2 to number 3? What is happening? So we can look at 3x minus 12 plus 12. We have x plus 4 plus 12. We've added 12 to both sides. Addition, property of equality. So I can go on, but let's just look through it. So addition, property of equality. The next line says simplifying. So you're going to take number 3 and simplify to line 4. So 3x minus 12 plus 12 is 3x. x plus 4 plus 12 is x plus 16. So we've simplified. So what is the difference between 4 and 5? Well, 3x minus x, we've subtracted. So you can say we subtracted from each side. How do I get from here to here? They say simplify that. It's given to you. So we simplify to this. How do we get to here? We divided. And then we have what we proved at the end. Again, you should come to class. We will cover this whole thing in class. I will give you an hour to ask any questions, and hope this helped you out.